Now we will talk about accuracy and error in measurement. Whenever we perform any experiment, then we have some sort of error. So the difference of true value and measure value of any physical quantity is known as error. Error are classified in two groups. First, due to cause of error. In this category, we place systematic error, random error, and gross error. And second is due to the magnitude of the error. In this category, we place absolute error, mean absolute error, relative error, and percentage error. For absolute error, we have to know the exact value. If the exact value is not given, then we perform experiment and take some readings. The average value of all readings will be called as real value or mean value. Let if the readings are A1, A2, A3, so on AN, then the real value will be A1 plus A2 plus A3 plus so on AN divided by N. Now, the absolute error will be equal to the difference of mean value or real value and the reading taken by us. So, the absolute error in first reading will be del A1 equal to A mean value minus A1. For second, A2 equal to A mean value or real value minus A2. For nth reading, absolute error AN equal to real value minus AN. Now, the mean absolute error is known as del A bar. This will be equal to the mean value of all absolute error. So, the mean absolute error del A bar is equal to del A1 plus del A2 plus so on del AN divided by N. For this, we have to use the numerical value only. Now, take relative error. Relative error is equal to the ratio of mean absolute error to the real value of the physical quantity, which will be A mean value. For percentage error, we just have to multiply this with 100. Del A average divided by AM multiplied by 100, and this will be in percentage. In physics, for getting the value of physical quantity, sometimes we have to multiply, divide, add, subtract some sort of physical quantities. And if we have the errors in all particular quantities, then what will be the error in the desired physical quantity? We don't know how to get this. So here is the heading: combination of error. First, we will learn about error in sum of the quantity, which will be same for error in difference of the quantities. Let a physical quantity x is equal to sum of physical quantity A and B. Let for A, del A is absolute error in A, and del B is absolute error in B. Similarly, del X is absolute error in X. In this case, the equation 1 can be written with error as x plus minus del x equal to a plus minus del a plus b plus minus del b. Now, if we open this, or a plus b plus minus del a plus minus del b. Since a plus b is equal to x, so we can write here x and x will be cancel this. So plus minus del x equal to plus minus del a plus minus del b. Now, if we choose the sign, then we can have four possible values, which will be for this plus del a plus del b plus del a minus del b minus del a plus del b minus del a minus del b. Here we can say clearly that this both are adding, this both are adding. So the maximum permissible error will be this and this, not this. So maximum permissible error plus minus del x will be equal to plus minus del a plus del b. Here we get both value del a plus del b minus del a minus del b. So this is the error in sum of the quantities. For when we add two quantities, then we have to just add the errors. And similarly, for difference or subtraction of the quantities, we get the same result. Now let's take an example. In an experiment, capacity of two capacitors are measured as 1.3 plus minus 0.1 microfarad and 2.4 plus minus 0.2 microfarad. When both capacitors are connected in parallel combination, then find net capacity with percentage error. So when we connect capacitor in parallel order, then net capacity will be given as Cp equal to C1 plus C2. Here C1 equal to 1.3 plus minus 0.1 microfarad. 0.1 is mean absolute error. C2 is 2.4 plus minus 0.2 microfarad. So we can see that here is a combination of two physical quantities. So the exact value Cp will be 1.3, this one plus this one 2.4, which will be equal to 3.7 microfarad, and the error will be equal to, we know that there is a sum of quantity. In this we have known that error will be del C1 plus del C2. So the value is 0.1 plus 0.2, which will be 0. Plus minus 0.3 microfarad. So the exact value will be written as Cp equal to, original value is 3.7 plus minus error 0.3 microfarad. If we want to know percentage error, then the percentage error is equal to mean absolute error, which is del Cp divided by original value Cp into 100. Del Cp is 0.3, Cp is 3.7 into 100. It almost come to 8.1%. So if we write this in percentage error, then Cp is equal to 3.7 plus minus 8.1%. As I told you that error for sum of the quantities and the difference of the quantities will be same, and similarly error in product of the quantity and division of the quantities will be same. Let physical quantity x is equal to a multiplied by b, and absolute error in a is del a, absolute error in b is del b, absolute error in x is del x. Then with error we can write equation 1 as x plus minus del x equal to a plus minus del a multiplied by b plus minus del b. Now take x out of this bracket, a out of this bracket, b out of this bracket. In this case we get x 1 plus minus del x divided by x, because we want to take x as a common, but there is no x, there is del x, so we have to multiply x and divide x. Here a 1 plus minus del a divided by a, b 1 plus minus del b divided by b, or a into b bracket 1 plus minus del a divided by a bracket 1 plus minus del b divided by b. By using equation 1 we get eb is equal to x, and this x will cancel this, so 1 plus minus del x divided by x equal to, just open this box, multiply them, and we get 1 plus minus del a divided by a plus minus del b divided by b plus minus del a divided by a del b divided by b. As we know that the error are smalls, so here del a upon a and del b upon b are very small, they are so small, so if we multiply them then this quantity will be extremely small compared to them, so we can neglect them. If we neglect this then we get, and this one will be cancelled with this, so we get plus minus del x divided by x equal to plus minus del a divided by a plus minus del b divided by b. Now again we have four possible value of this relative error. This is relative error, this is relative error, this is also relative error. So we have four possible value, which are del a divided by a plus del b divided by b, del a divided by a minus del b divided by b, minus del a divided by a plus del b divided by b, minus del a divided by a minus del b divided by b. Now the maximum permissible relative error are this and this. So the maximum permissible relative error in the desired quantity will be plus minus del a divided by a plus del b divided by b. If we want percentage error, then just multiply this with 100. Okay. Now we have to find the error in quantity raised to some power. Let the quantity x is given by a to power m divided by b to power n. Here we get, here we use some term which we are not familiar, but later we will be known about them. First we have to log this equation. If we take log both sides, then we get log x is equal to log a to power m divided by b to power n. In log, we have the formula log a divided by b equal to log a minus log b. So we can write this log a to power m minus log b to power n. Again, we use the identity of log. Log a to power m is equal to m log a. So m will be go here, m log e a minus log e b, here n. Now differentiate this equation and we get dx divided by x equal to m dA divided by a minus n dB divided by b. In term of relative error, we can write this plus minus del x divided by x m plus minus del a divided by a minus plus n del b divided by b. So here again we have four possible value. So the maximum permissible error will be del x upon x equal to plus minus m del a divided by a plus n del b divided by b. We will take an example so we can understand them better. Here we have example. Resistance is given by R is equal to V upon I, where V is equal to 100 plus minus 5 volt and I is equal to 10 plus minus 0.2 ampere. Then find percentage error in R. Since R is equal to V upon I, here the error will be due to the division of the quantity, and we know that in division of the quantity relative error of R del R divided by R will given by del V divided by V plus del I divided by I. Okay, but we want to know the percentage error in R. So for percentage error we have to just multiply this with 100. This will be in percent. So we get del V 5, the original value is 100 into 100 plus del I is 0.2 divided by I, which is 10, multiplied by 100, and we get 5% plus 2% equal to 7%. So the percentage error in R will be 7%. The next example is if Z is given by a to power 4, b to power 1 by 3 divided by c d to power 3 by t, then we have to find the relative error in Z. Here the error is due to the power, and we know that in power relative error of Z is given by del Z divided by Z equal to, first we have a to power 4, this 4 will be multiplied and a will be del a divided by a plus b to power 1 by 3, so 1 by 3 will be multiplied del b divided by b, c to power 1, so 1 will be multiplied and we get del c divided by c, d to power 3 by 2, so 3 by 2 will be multiplied and we get del d divided by d. So this will be the error, relative error of Z. Our next topic is significant figures. What are significant digits? So what are significant digits? Significant digits or significant figures are the digits which show accuracy or preciseness in our result. For finding the significant figure, we have some rules like all non-zero digits are significant. For example, in the result 2.342. In this, we have 1, 2, 3, 4, 4 significant digits. Second rule is the zeros appearing between two non-zero digits are significant. For example, if we have example 2.0034, then in this case there are, this is non-zero, this is non-zero, and these two zeros are between two non-zero digits. In this case, this zero will be counted as significant. So the significant digits will be 1, 2, 3, 4, 5. Okay. Third and fourth rules is if the digit is less than 1, then all zeros appearing at left of the last non-zero digit are not significant. And fourth rule is trailing zeros after decimal places are significant. For example, we have a 0.0060. In this case, this 0, which is trailing 0, this will count as significant, but all 0 occurring to the left of the non-zero digits, these zeros will be not significant. So in this example, the number of significant digits will be 1 and 2. Next rule is the power of 10 are not counted as significant figure. In this case, let 1.4 into 10 to power 3, 4, minus 4, anything. In this case, the significant digit will be 1.1 and 4. So, digits are 2. Okay. Next rule is change in unit of measurement of a quantity does not change the number of significant figure. For example, 7.2 centimeter. In this case, we have two significant digits. If we change the unit, if we convert it in meter, then we get 0.072 meter. Again, in this case, the significant digit will be 2, as this is belong to the our third rule. Next rule is the number in which there is no decimal, then all 0 right side of the last non-zero digit will be not significant. But if there is unit behind it or it is obtained through measurement, then zeros will be significant. For example, 2040. In this case, we have three significant digits 2, 0 and 4. This 0 will not count as significant, but if this is obtained through a measurement like 2040 meter per second, 2040 meter per second, then in this case the significant digit will be 4. Our last topic of this chapter is rounding of the digit. For rounding of any digit, we have already studied the rules in small classes. So here we will learn them by example. Here I have choose 5 example. In all these example, I will rounding off this for 2 digits. For first example, let I have to round off it. If the digit which has to be round off and after this the number is less than 5, then we will retain is such as 7.8. Okay. If the number is greater than 5, then the preceding number will be increased by 1. In this case, the number will become 7.9. and the number which has to be rounding off if after this there is a number of 5 and after this there is non-zero digit, then the number will be increased by 1. So here in this case the number become 12.7. If after the 5 the number is 0 and before this the number is even number, then the number remains same. So in this case the after rounding off digit become 3.2. If after 5 number is 0 and before 5 number is odd number, then in this case number will increase by 1. So in this case number become 1.8 after rounding off.